Today, today we're going to look at some uh, examples and the definition of derivatives of inverse functions. So this is like your I do section. Um, I'm going to give you time today to complete the related rates problems from yesterday and to take these notes. Tomorrow you will have some practice problems, the we do and the you do for inverse functions, and the topic of Newton's method of approximating zeros will be next on the docket and also available to you tomorrow. This weekend you'll have a mix of review problems for this unit, and we'll be working with those at the beginning of next week. So for my white group, that'll be Tuesday for you, and my blue group, that'll be Wednesday when we look at those together. I'll also be holding optional office hours on Tuesday, but we'll discuss that further during class to figure out what time works for people. So take a moment and write down this definition of the derivative of an inverse function. All right. So this is one way to write the derivative of an inverse, right? Where g of x is equal to the inverse of f of x. All right. So this is an alternate way to write it. So kind of like the limit definition had two forms, we have two forms for writing the derivative of an inverse. So we're going to kind of switch between those forms today and see how they are equivalent to one another and how they are useful in different circumstances. So this first problem or example, we're going to look at using the alternate form. So consider the differentiable function f of x with the inverse f negative 1 of x, where f of x goes through the point 1, 6. So this would be an x, and this would be an f of x. And the derivative of f at 1 is 10, right? So that would be the instantaneous rate of change at x equals 1 is 10. What's the instantaneous rate of change of the integral? What's the instantaneous rate of change of the inverse? All right. So we're considering this point here. So inverses, if you remember from our earlier work, swap our input and output, because an inverse takes us from what we get in our original function back to what we had plugged in. So for our inverse, we swap our point, and we're looking now at 6, 1. So if we're looking at our alternate definition of the derivative, we're considering the derivative of f of negative 1 x dx. All right. And then we have to think about what point we're evaluating it at. But this is two ways we could write that derivative. We're going to be considering this when our value of the input for the integral, for the inverse, I don't know why I keep saying integral, is 6. So we're going to be looking at our inverse's instantaneous rate of change when x, our input for that inverse, is 6. So using our definition here, we've got the derivative when we are looking at our inverse at that value. So I'm going to have 1 over f prime, and then the inverse at 6 is 1. And then f prime at 1 is 10. So we have our answer here. All right, let's consider the next one. All right, same idea. We're thinking about what we know about the inverse. So we're going to first establish what the point is for the inverse, and then we're going to find the derivative of the inverse. So we're given the original function f of x with the point input of 3 and an output of 8. When we're considering the inverse, we've got those values swapped. So our x and our y have switched, our input and our output have swapped. So now we can consider, this should have a -1 here, sorry. Using the information that's given, some characteristics about our inverse. So the first characteristic we've identified is we're looking at this point, right? We've swapped that input and output from our original function, so that's good. Now let's see what we've got going on with our derivative of the inverse. All right, at that input we've got for our inverse 8. Using our definition, I've got 1 over f prime, right, with my inverse on the inside. We're looking at 8, our input for that inverse. So I've got 1 over f prime, and the inverse's value at 8 is 3, and we're given f prime of 3 is 5. So we now know the slope of our integral at our input of 8 is this. Our other name for that would be our instantaneous rate of change. Oh, look at that, I fit it in there. All right. This next one is going to have us considering the other form. So the other form has g prime of x equal to 1 over derivative f at g of x. So this is another way of writing the same thing. So if we're looking for g prime of 6, we're going to look for 1 over the composition of the original function, f prime, original function's derivative, f prime, with our inside function being g of x. So I've got 1 over f prime of g of 6, which is I have to establish more information for you. So g of x is equal to the inverse of f. All right, so that means when we've got these points here of 2, 6 for f of x, we've got the point 6, 2 for our inverse, and 8, 6. Those are swapped, right? So if we're looking at the inverse at 6, our input of 6 gives us an output of 2. So once again, all I've done is I've swapped these two, my input and my output, when I'm thinking about my inverse's points. So we need to do that step first before we can figure out the derivative of that inverse. So then I'm looking at the f prime, or the derivative of f of x, at 2, and that's 1/3. Multiply by the reciprocal, and you get 3. All right, we've got another example here, and then some inverse trig rules. All right, this one, once again, is in the original notation. All right, but instead of g, it's using h. So h prime is equal to 1 over our original function, f prime of h at that point. All right, so I'll do it in this form, and then I'll just write it again in my alternate form on the right-hand side in a different color. So for this one, we're told that h and f are inverses. So h of x is the same as saying the inverse of f of x. We don't have to do any swapping of values this time because they were kind enough to give us some values here to work with. Sorry. All right, so our inverse has the points -4, 1, and 1, -2. All right. So we're considering h prime of -4. So that's going to be 1 over the derivative of f for h of 4. So we've got 1 over derivative f of h of -4. What's that, -4? Which is 1. And the derivative of f at 1 is 4. So we've got 1/4. If we were to do that in our other notation, which uses f inverse, it would be the same exact math. It would just look different along the way. So 1 over, this one would be f prime, f -1, x. All right. Same process, right? Because this h here for my inverse, the other name for it is f -1 of x. So when you're looking at this guy, we're still looking at -4. You have 1 over the derivative f when the inverse has an input of -4. And the same exact math applies, so it's going to be 1 over f prime. The output at -4 for our inverse is still 1, and the derivative of f at 1 is still 4. So they get you to the same place, it's just a difference in notation. And then we have our inverse trig rules. All right, we're not going to go through the proofs for all of these. For now, just write them down. The practice problems you'll get for tomorrow and the you do problems you get will include inverse trig problems in addition to the inverse problems like we did today in these notes. Have a great day, folks.